We propose OpenBox, an automatic open vocabulary annotation for 3D object detection. Conventional 3D object detection models are typically trained in a closed-set setting using datasets annotated by humans. However, this leads to two drawbacks. At inference time, they fail to detect novel class objects, and human annotation is very expensive and time-consuming. Meanwhile, in the 2D domain, vision foundation models trained on large-scale text-image aligned datasets have emerged. However, in 3D perception, obtaining large-scale datasets is difficult, and annotation is non-trivial, which acts as a bottleneck. Therefore, we propose a pipeline that leverages 2D vision foundation models to automate the annotation for 3D object detection. Our contributions are as follows. Given only time-synchronized ego pose, images, and LiDAR point clouds, our two-stage pipeline automatically annotates high-quality 3D bounding boxes. As a result, we achieve state-of-the-art performance across diverse autonomous driving datasets, including Waymo, Lyft, and in-use scenes. First, given multi-frame LiDAR point clouds, text prompts containing the target classes to be annotated, and images. We leverage 2D vision foundation models to extract instance-level information. We then associate it with the 3D point cloud to obtain an instance-level point cloud. However, as shown in the figure, backgrounds such as guardrails make it difficult to obtain a point cloud that contains only the instance, which in turn leads to bounding boxes with incorrect sizes. Therefore, in addition to the instance-level point cloud, we also use point clusters obtained after ground removal and HDB scan clustering. We remove background points by matching the previously obtained point cloud clusters to the instance-level point cloud, computing their inclusion ratios, and retaining only those clusters whose ratios exceed a specified threshold. Next, we adaptively annotate the bounding box according to the instance's physical properties. First, for the static object, instance-level point cloud aggregated over multiple frames, we suppress noise by majority voting with the vertices of a mesh reconstructed via a signed distance function. After that, we use instance size statistics obtained via ChatGPT to generate two candidate boxes using instance mesh's normal vector direction. We then project both candidates into 2D, compute their IOU with the box predicted by the 2D vision foundation model, and select the candidate with the larger IOU as the final bounding box. For rigid dynamic objects, we refine the box within a single frame by splitting into two cases. We compute the dot product between the ray from the LiDAR to the center of the initial box and the normal vector of the initial bounding box. If the value is negative, we extend the box in the opposite direction along that normal. We trained models on our auto-annotated dataset and evaluated 3D object detection performance on a human-annotated validation set to compare with other automatic annotation methods. As shown in the table, OpenBox outperforms the baselines, which we attribute to adaptively constructing bounding boxes according to each object's physical properties by leveraging instance information. Similarly, under the same settings, OpenBox outperforms the baselines on other datasets, and the advantage holds in direct comparisons on the training set as well. This suggests that, rather than merely summing per-modality boxes by distance as the baseline does, our approach leverages the different modalities more effectively. Next, we present qualitative results. Scenario 1 compares other automatic annotation methods, OpenBox, and human annotations. As shown in the video, our method produces fewer false positives and achieves more accurate localization than the baseline. We observe that the method maintains strong performance even in crowded, complex pedestrian scenes. Next, we present results for annotating novel classes that are not labeled in the Waymo Open Dataset. Our method successfully annotates objects that can become obstacles in driving scenarios, such as trash bins. We also observe that traffic cones are also annotated effectively.